ring like a bell or, hum like some giant tuning fork, or maybe even warp the very fabric of space around it. And here's the really audacious part. What if we could actually tap into that energy?
Welcome to the Deep Dive. This is where we take your most fascinating questions and, well, we dive deep into the science to find the answers. And today, we're doing exactly that. We're exploring this pretty wild concept, harnessing energy from an Earth-sized standing wave.
Right. So our mission today is to really dissect this idea. It sounds like science fiction, right? But we're going to break it down into 3 different physical interpretations. We've got mechanical, electromagnetic, and gravitational. We'll look at, how feasible they are, the kind of energy we're talking about, and the just colossal implications if we try to actually harvest our planet's deepest rhythms. We want you to get all the crucial insights without getting totally bogged down in the super technical stuff.
Yeah, get ready for hopefully, some real aha moments. We'll unpack what's genuinely real here, what might be theoretically possible, and let's be honest, what's still firmly in the realm of science fiction. By the end, you should walk away pretty well informed and with plenty to think about.
Okay, so if we're talking about tapping into Earth's deepest rhythms, where do we even begin? I guess the most sort of tangible place is right under our feet. The planet's own vibrations.
Exactly. That's the most grounded interpretation. Seismic-free oscillations. Think about it like this. After a huge disturbance like a massive earthquake, the Earth literally rings like a bell. And it can go on for weeks, even months sometimes.
Wow.
And these aren't just random shakes. We're talking about global standing waves. They're called normal modes. They're created by seismic waves, body waves and surface waves circling the entire globe. Their wavelengths are quite literally the size of Earth's circumference. It's pretty amazing.
Okay, so the whole planet is vibrating in these massive waves. Are there different kinds?
Yes, good question. We mainly categorize them into 2 types. First, you have what are called spheroidal modes. Think of the label NSL. These are complex. They involve both up and down, sort of radial motion, and side-to-side transverse motion.
Oh, wow.
And because they actually change the Earth's shape and volume slightly, they cause tiny, tiny perturbations in the planet's gravitational field. This means we can detect them, but you need incredibly sensitive instruments, seismometers, strain meters, even gravimeters.
Right.
A couple of famous examples. There's the 0S2 mode. Nickname is the football mode.
Yeah. Okay.
It has a period of about 54 minutes, and it basically deforms the Earth into something like a slightly squashed or stretched football, a prolate or oblate spheroid.
54 minutes for one oscillation. That's slow.
Incredibly slow from our perspective. And then there's the 0-0 mode, the breathing mode. That's about 20.5 minutes. The entire planet just uniformly expands and contracts like it's taking a slow breath.
So the Earth is literally breathing and bulging like a football. That's wild. Would we feel that, or is it too small?
Oh, no. On an everyday scale, you wouldn't feel it directly at all. Far too subtle. But the instruments, they absolutely pick up those minute changes. Now, the other main type is the toroidal mode, or NTL. These are different. They're purely shear motions.
Shear motions.
Yeah, meaning the movement is entirely horizontal, and it's perpendicular to the direction the wave is traveling. Think of it like twisting. The crucial difference here is that these modes cause no change in volume or density, so they don't perturb the gravitational field.
Ah, okay, so they're harder to detect then.
In some ways, yes. Harder to detect with gravimeters, for instance. Yeah. But they're incredibly important for scientists trying to figure out the structure of the deep mantle because they travel right through it.
Okay, that makes sense. So where does the energy come from to make the Earth ring and breathe and twist like this? It can't just be the big earthquakes, can it?
Well, earthquakes are definitely the big hitters. But you're right, there's a fundamental duality here. Without a doubt, the most powerful excitation comes from those transient high-energy events. We're talking megaquakes, moment magnitude greater than 8.0. That scale better reflects the total energy released.
Right, the really catastrophic ones.
Exactly. These things release immense strain energy built up in the crust, and that energy excites a whole broad spectrum of these normal modes. We can see them ringing for weeks, months even. We got some incredibly clear recordings after the 2004 Sumatra-Andaman earthquake that was a 9.1 to 9.3, and the 2011 Tohoku quake in Japan, a 9.0 to 9.1.
I remember those. Devastating.
Absolutely. And just to give you an idea of the scale, after that Sumatra event, the 0S2 football mode, its initial amplitude was over 0.1 millimeters globally. And as the main surface waves, the Rayleigh waves, swept across the planet, the ground actually moved up and down by more than a centimeter in places.
A whole centimeter globally. That's a huge amount of movement when you think about the entire planet.
It really is.
Yeah.
But here's the other side of that duality you mentioned. The Earth isn't just ringing after these huge quakes. It's actually always vibrating at a very low level. There's a sort of background-free oscillation. People sometimes call it the Earth's hum.
The Earth's hum. What causes that?
It's thought to be mainly caused by ocean waves, specifically what are called infragravity waves. They interact non-linearly with the seafloor, especially along coastlines, and continuously couple a tiny amount of energy into the solid Earth.
Huh. So the oceans are constantly plucking the planet, making it hum.
That's a good way to put it. Now, the amplitudes are minuscule. We're talking around 0.5 nanogals. A gal is a unit of acceleration, so a nanogall is incredibly tiny, like the gravitational pull of a speck of dust from a few feet away.
Wow.
But here's the key. It's a continuous power source, always there.
So you've got these massive but rare energy spikes from quakes and this constant but incredibly faint background hum.
Exactly. And that duality, the colossal but unpredictable versus the faint but continuous, is what makes the whole energy harvesting idea so, well, interesting and so challenging. Let's try and quantify that energy. The 2011 Tohoku quake, estimates are around 1.75 times 10 to the 17 joules of strain energy released. Pretty consistent with the radiated seismic energy, about 1.9 times 10 to the 17 joules.
That sounds like a lot of zeros.
It is. The 2004 Sumatra event was even bigger, maybe closer to 10 to the 18 joules. Now compare that to global human energy consumption.
Okay. Yeah, I can see the incentive there. Even a fraction of that is huge.
It's a powerful incentive, for sure. But that duality we talked about, it dictates the whole approach. Any realistic extraction system would have to be hybrid. You'd need some kind of standby peak capture mode, ready to grab that massive energy burst after a quake, which only lasts for weeks or months as it decays. And you'd need a continuous harvesting mode, trying to siphon off energy from that faint background hum all the time. That really shapes the engineering architecture you'd need.
Those energy figures, especially from the big quakes, they're just immense. But how on earth literally do you even begin to capture something that's so huge, but also so fleeting and unpredictable, and then also capture that tiny hum? What would the actual, structure for this even look like?
Yeah, you're hitting the absolute core challenge there. The conceptual idea, let's call it the Geonet harvester, the basic principle is simple enough. Convert that mechanical strain, the stretching and squeezing of the Earth's crust and mantle, directly into electrical energy.
Okay, convert strain to electricity. Where would you put these things?
Ideally, you'd target the antinodes of the lowest frequency spheroidal modes. Those are the spots where the ground displacement and the strain are maximum for those big planet-scale oscillations.
So we're talking about building something into the planet. What kind of tech could possibly do that? We're not talking about solar panels here.
Definitely not. We'd need massive extrapolations of technologies that exist, but on a completely different scale. Think about piezoelectric systems.
Piezoelectric? Like in lighters?
Sort of, yeah. Materials like PZT ceramics generate a voltage when you squeeze them, when they're under stress. You could embed huge arrays of these deep in the crust. Or maybe electromagnetic systems. Imagine anchoring a massive magnetic core deep down and having a coil attached to a shallower rock layer. As the Earth vibrates, there's differential motion.
Which induces a current in the coil, like a giant generator using the Earth's own movement.
Exactly. But again, the scale is just mind-boggling.
So this Geonet harvester, it wouldn't be just one device. It sounds like a global grid.
Precisely. You'd need a global grid, thousands of deep boreholes, drill down kilometers, probably into stable continental areas, what we call cratons. And each borehole would have a vertical stack of these transducer modules, whatever they turn out to be, piezoelectric, electromagnetic, maybe something else.
And the whole grid would have to be geographically placed just right to hit those antinodes?
Optimize, yeah. To target the known antinodes of the most energetic modes, like that zero-stew football mode. And then, of course, you need to get the power out. That means a planetary scale smart grid, probably using high voltage direct current, HVDC, because that's much more efficient for transmitting huge amounts of power over vast global distances.
The challenges just sound immense. What's the biggest single hurdle?
I'd say the primary one is what we can call the low frequency challenge. Earth's fundamental modes, they vibrate in the millihertz range, remember, periods of minutes to an hour.
Right, super slow.
Yeah. And most energy harvesters we have today, they're designed for much higher frequencies, vibrations per second, maybe 10 hertz or more. They're incredibly inefficient in millihertz.
So we'd need completely new designs.
Revolutionary designs, really. Things that don't exist at this scale. Maybe mechanisms for frequency up conversion, like using the slow Earth motion to pluck something that vibrates much faster, or using nonlinear resonance tricks, systems designed to strongly resonate even with very slow, weak inputs.
And just the materials and the drilling.
Oh yeah. Beyond the physics, you've got material science and geotechnical engineering on an unprecedented scale. We're talking about needing cubic kilometers of advanced materials, a global industrial effort that would absolutely dwarf anything we do now in mining or deep-sea drilling.
It sounds almost impossible, but the payoff. You mentioned the energy numbers.
The potential power is staggering, yes. Let's go back to that Tohoku earthquake example. If you could capture the energy from its decaying oscillations with just 1% efficiency over, say, the first month.
Okay, 1% efficiency.
You'd be looking at an average power output of around 670 gigawatts.
670, that's roughly the total installed electrical capacity of the entire United States, isn't it?
Pretty much, yeah. From one earthquake event captured at low efficiency, it shows you the scale of the energy available.
But I mean, could you ever justify such a colossal undertaking just for the energy? The cost would be astronomical.
That's a crucial point, and it leads to what really changes the potential equation. The dual-use justification. You're right, a project of this magnitude could likely never be justified by energy production alone. The economics probably wouldn't work, not for a long, long time.
Okay, so what's the other use?
Think about it. This global network of thousands of deep, sensitive transducers. It would inherently be the most advanced global geophysical monitoring system ever conceived. By far. It would give us real-time, high-resolution maps of strain and stress accumulating in the Earth's crust, everywhere, all the time.
Ah, so it's also an earthquake and volcano prediction system on steroids?
Potentially, yes.
Yeah.
Or at least a vastly improved understanding and forecasting system for all sorts of geohazards. So this dual capability, clean energy plus a revolutionary leap in fundamental Earth science and hazard forecasting that fundamentally changes the value proposition. The scientific and societal value of the data alone might be comparable to the economic value of the energy.
That does change things. But with that kind of power, literally altering the Earth's vibrations, there have to be risks, huge risks. What are the potential consequences if we start, messing with Earth's natural rhythms?
The consequences could be profound, absolutely. If you're actively damping these global oscillations, you're removing mechanical energy from the system. That could potentially alter seismicity patterns, change stress fields in the crust. Maybe it leads to fewer earthquakes overall, but the ones that do happen could be more powerful megaquakes because stress has been allowed to build up for longer without smaller release events.
Okay, that's worrying.
Or, maybe worse, if the energy extraction isn't perfectly uniform across the globe, and how could it be? You might trigger earthquakes in regions we currently think of as stable just by redistributing the stress in unforeseen ways.
It sounds like we'd be playing planetary billiards with tectonic plates.
That's not a bad analogy. And it gets even more, alarming.
How so?
Remember, this whole GeoNet harvester system is designed to resonate with Earth's natural frequencies. That's how it extracts energy efficiently.
Right.
So, what happens if the control systems fail? What if there's some unforeseen positive feedback loop? Maybe a massive surge from the global power grid somehow gets coupled back into the harvester network.
You mean instead of extracting energy, it starts pumping energy in?
Exactly. You could potentially initiate a runaway seismic resonance, pushing the planet harder and harder at its natural frequency.
What would that do?
It could destabilize continents. It could, in the most extreme scenario, maybe even shatter the crust. In that nightmare scenario, the energy harvesting system transforms into a planetary-scale weapon, intentional or not.
Okay, that's genuinely terrifying. The fail-safe design for something like this would have to be the absolute top priority, more important than the energy itself.
Without question, it would be the single most critical engineering and ethical challenge of the entire project, assuming it ever got off the ground.
Right. Okay, let's shift gears a bit. From the solid Earth ringing beneath us, let's look up into the atmosphere. You mentioned other standing waves.
Yes. There's another global standing wave phenomenon happening constantly right around us in the atmosphere. These are the Schumann resonances.
Schumann resonances. Okay, what are they?
Well, think about the space between the Earth's surface and the ionosphere, which starts about 80 to 100 kilometers up. That whole cavity acts like a natural spherical waveguide, like a resonant chamber.
Okay, a cavity between the ground and the upper atmosphere. What makes it resonate?
Lightning. There are about 2,000 thunderstorms active around the globe at any given moment. That generates something like 50 lightning flashes every single second.
Wow, that many.
Yeah, it's continuous global electrical activity. And all that lightning excites this Earth ionosphere cavity, creating extremely low-frequency ELF standing waves. Those are the Schumann resonances.
So the whole atmosphere is sort of humming with these ELF waves from lightning. What kind of frequencies are we talking about?
Very low. The fundamental mode, the main one, is around 7.83 hertz, so just under 8 cycles per second. Then there are higher harmonics, around 14.3 hertz, 20.8 hertz, 27.3 hertz, and so on. And these frequencies aren't perfectly stable. They fluctuate slightly depending on what the ionosphere is doing, day-night changes, solar activity, that kind of stuff.
Okay, 7.83 hertz, still very low frequency. Now, the big question, energy harvesting. Can we tap into this atmospheric hum?
Well, while it's a fascinating phenomenon, and it's definitely real, here's the immediate stark reality for energy harvesting. This avenue. It's pretty much a physical and engineering dead end for any large-scale power.
Oh, why is that?
The fatal flaw is the energy density. It is just incredibly, incredibly low, vanishingly small. The electric field component is only about 300 microvolts per meter. The magnetic field is around 1 picotesla.
Microvolts and picoteslas, those sound tiny.
They are extremely tiny. It translates to a power density, the amount of power flowing through a square meter, of about 2.4 times 10 to the minus 13 watts per square meter.
Okay, 10 to the minus 13. That's a decimal point followed by 12 zeros and then a 24. That is minuscule. Can you, put that in perspective?
Sure, let's try. If you wanted to power just one standard LED light bulb, let's say it uses 1 watt, you would need a collector array, an antenna system, roughly the size of Peru.
The size of Peru for one light bulb?
Yep. Want to power an average American home, about 1.2 kilowatts, you need a collector area about 1.5 times the size of India.
Okay, this is getting ridiculous.
It gets better. Want to power a large gigawatt-scale power plant? Your collector would need to be 8,200 times the total surface area of the Earth.
Right. Okay. Point taken.
Yeah.
So Schumann resonances for energy harvesting are not happening.
Definitely not for macro-scale power. It's a classic example of something that's scientifically interesting but energetically useless for our needs. As you said earlier, it's not a vast well of energy. It's more like a tiny cup that's constantly being refilled by lightning. If you somehow built a giant collector, you wouldn't be tapping a huge source.
No.
You'd just be damping the existing resonance, reducing its amplitude.
So if not for energy, what's the value? Why study them?
Their value is primarily informational. Because the resonances are global and sensitive to global lightning rates and ionospheric conditions, they act as a kind of natural thermometer for the planet's electromagnetic environment. Scientists use them to monitor global lightning activity, probe the ionosphere, and maybe even track some climate-related trends. It's a global information carrier.
Okay, so no energy, but still scientifically useful. But let's run the thought experiment anyway. What if we could somehow damp these resonances significantly? What would the global consequences be? We're talking about messing with the background EM field of the planet.
Yeah, it's an interesting thought experiment. Even though it's impractical for energy, considering the consequences is important, you could potentially impact atmospheric chemistry. Altering the global ELF environment might affect things like ozone concentrations, maybe similar to how changes in the Earth's main magnetic field can let more high-energy particles in. Could it shift weather patterns, maybe even trigger some cooling? It's speculative, but possible.
And what about life? We evolved in this environment.
That's a really profound point. Life on Earth evolved over billions of years bathed in these natural electromagnetic fields, including Schumann resonances. We know many species, sharks, sea turtles, salmon, lots of migratory birds, use the Earth magnetic field for navigation. There's evidence some might even be sensitive to Schumann resonances, too.
So messing with it could throw them off.
It could potentially disrupt migration routes, maybe affect predator-prey dynamics. Who knows what cascading effects that could have on entire ecosystems. It raises a sort of philosophical challenge, too. What one field of science might dismiss as background noise, another might recognize as a vital environmental signal. Damping Schumann resonances, even if you could, might be seen as a form of global environmental pollution by omission, removing a key natural signal that's been part of the biosphere forever.
Pollution by omission. I like that framing. Okay, so seismic waves have potential but huge challenges and risks. Schumann resonances are a non-starter for energy. Where else can we look? Our final deep dive takes us into the most speculative territory yet, right? Draining space-time itself, theoretical standing gravitational waves.
Yeah, now we're really pushing the boundaries into theoretical physics and cosmology. The idea here is a standing wave in the fabric of space-time itself. We know from Einstein's general relativity that accelerating massive objects create ripples in space-time gravitational waves. We've detected these traveling waves, famously from colliding black holes and neutron stars.
Right, LIGO and Virgo detections, huge news.
Exactly, but a standing gravitational wave, that's different. That would be an interference pattern formed maybe by two identical gravitational waves traveling in opposite directions.
Right.
And that is purely theoretical at this point. We have absolutely no observational evidence for such a thing.
What would even create one? Colliding black holes make traveling waves. How do you get a standing wave?
That's the first massive hurdle. Gravitational waves interact extremely weakly with matter. They mostly just pass right through things, so they don't reflect easily like light waves off a mirror. To get a standing wave, you'd need one of two incredibly unlikely scenarios. Either you'd need perfectly synchronized, incredibly powerful sources. Imagine two identical binary black hole mergers going off at just the right places and times to create interfering waves. The chances of that happening naturally are basically zero.
Okay, so not natural sources. What's the other option?
Exotic boundary conditions. You'd need some kind of hypothetical mirror for gravitational waves, maybe something like cosmic domain walls, which are theoretical boundaries between different vacuum states of the universe predicted by some speculative physics theories like brane worlds.
Brain worlds, not domain walls. Okay, we are definitely beyond the standard model of physics now.
Way beyond. These are highly speculative ideas, completely unobserved. So the very formation of a standing gravitational wave is already deep into unknown physics.
But let's assume, for the sake of argument, one exists. We know traveling gravitational waves carry energy. We see that in binary pulsars losing energy exactly as predicted. Could we theoretically tap into the energy of a standing gravitational wave?
Well, theory does suggest gravitational waves transport energy. But actually localizing that energy, saying the energy is right here, is notoriously tricky in general relativity. It's not straightforward. However, theoretical studies suggest energy transfer might be possible under really extreme conditions.
Like what?
Maybe if you had a huge volume of incredibly viscous fluid placed just right in the standing wave pattern. The oscillating spacetime could induce shear forces in the fluid, and that energy would dissipate as heat.
Heat from warping spacetime.
Or perhaps even more exotically, you could have resonant absorption by some form of exotic quantum matter. Imagine a vast cloud of, say, a maximally dense Bose-Einstein condensate made of bosons that can absorb gravitons, tuned perfectly to the wave's frequency.
Okay, so the potential mechanisms are themselves based on exotic physics and materials. What does that imply for actually building something to do this?
It implies that this scenario is firmly in the realm of science fiction, or at least the domain of a civilization far, far beyond ours. We're talking Kardashev Type 2 or Type 3 civilization here.
A civilization that can harness the energy of its entire star or its entire galaxy.
Exactly. The architecture would be cosmic. You'd need to introduce some kind of dissipative element into the oscillating space-time itself. Maybe it's a literal planet-sized shell of this engineered ultra-viscous fluid placed perfectly at an antinode of the standing wave, designed to get hot. Or maybe it's a nebula-sized cloud of this exotic quantum condensate tuned to soak up gravitons.
The engineering is inseparable from discovering entirely new physics.
Completely. The successful detection, let alone harnessing, of a standing gravitational wave would require, and therefore prove, physics way beyond what we currently know.
Yeah.
Its existence would be revolutionary.
And the consequences. If we're talking about tampering with the fabric of space-time on potentially cosmic scales, what are we even looking at?
The potential consequences are almost unimaginable. If you actively damped such a waves, you'd be altering the local geometry of spacetime. It would presumably relax somehow as the wave's energy was removed. What that would actually do locally, we have no real idea.
And what about the source, if it relies on something like a cosmic domain wall?
That's another huge risk. If this hypothetical standing wave is being supported or reflected by some exotic structure like a domain wall, extracting energy from the wave could destabilize the wall itself. A collapsing domain wall could release energy comparable to a supernova, or maybe even trigger a change in the laws of physics in that region of space.
Yeah.
So, besides the technological impossibility, there are cosmic-scale dangers.
And cosmic-scale ethical questions. If such a unique cosmological artifact, a standing gravitational wave, actually exists, would it be ethical to destroy it just for energy? It's like asking if we should dismantle a star or a black hole for fuel.
Right. It's not just ours to take. And then there's the mundane problem of waste heat, scaled up to cosmic proportions. Energy conversion is never 100% efficient. A system capable of interacting with and extracting energy from gravitational waves on this scale would inevitably generate absolutely colossal amounts of waste heat, enough to potentially alter the thermal balance of an entire star system. It's the ultimate thermal pollution problem.
It really puts things in perspective. There's also a fundamental point about stability here, isn't there?
Yes, in the theoretical models where these things might exist, a standing gravitational wave is generally considered a stable configuration. The act of extracting energy from it is inherently an aggressive transformative process. You're not just passively collecting energy, you are actively interfering with and ultimately destroying the wave itself. It's kind of analogous to how making a measurement in quantum mechanics collapses the wave function. You fundamentally change the system by interacting with it.
Okay, so let's try and pull all of this together. We've looked at three very different possibilities for harnessing Earth-sized or larger standing waves. How do they stack up in terms of feasibility?
Right, let's assess them on a spectrum. Standing gravitational waves. Feasibility. Effectively zero. It's pure theory, requires physics we don't have, and technology characteristic of a Kardashev type 2 or 3 civilization. Its value for us now is purely as a mind-bending thought experiment, pushing the edges of known physics.
Okay, zero for gravitational waves. What about Schumann resonances in the atmosphere?
Also zero feasibility, but for a different reason. Not because they aren't real, they absolutely are. But the energy density is just profoundly, irredeemably low for macro-scale power. You simply cannot build a collector large enough. It's physically real, but energetically useless for large-scale power generation. Its value is as a source of geophysical data.
Right, so that leaves the first one we talked about, seismic-free oscillations, the Earth ringing like a bell.
Exactly. And this one is different. I'd classify its feasibility as exceedingly low, but crucially non-zero.
Non-zero. Okay, explain that.
It's physically real. The Earth definitely rings. The energy involved, especially after large earthquakes, is energetically potent enough to be interesting, to warrant consideration. It doesn't require fundamentally new physics like the gravitational waves do.
Yeah.
And it's a huge but. It presents absolutely monumental engineering challenges, as we discussed. The low frequency, the materials, the scale, the control systems, the risks.
So it's the only one that's even remotely in the realm of possibility, however distant.
Pretty much, yes. It's the only one based on known physics and potentially accessible energy scales, even if the engineering is generations beyond us.
Okay, so if humanity ever decided this was worth pursuing, this monumental challenge of tapping seismic oscillations, what would a hypothetical research program even look like? This sounds like a multi-trillion-dollar, century-long kind of project.
Oh, absolutely. Minimum. You'd have to break it down into phases spanning decades, probably over a century. Phase 1, maybe the first 20 years, would be purely foundational science and maybe miniaturization, focusing entirely on overcoming that low-frequency challenge.
Right, making harvesters that actually work at millihertz.
Exactly. Discovering or engineering advanced piezoelectric or magnet-restrictive materials that are efficient at those frequencies. Developing and testing completely novel harvester designs in the lab, computational modeling, small-scale prototypes exploring those ideas like frequency-up conversion or nonlinear resonance.
Okay, 20 years of basic R&D. Then what, assuming some breakthroughs happen?
Then you move into phase 2, maybe years 21 through 50. This would be about pilot programs and critically global impact modeling. You need to move from the lab bench to the real world. Deploying, say, kilometer-scale pilot harvester arrays, maybe down deep mine shafts or in dedicated deep boreholes, just to get real-world data and prove the concept actually works outside the lab.
And the modeling part?
Simultaneously, you'd need a massive effort in developing incredibly high-fidelity, fully coupled Earth system models. These would need to integrate the solid Earth, oceans, atmosphere, ionosphere, everything to seriously simulate the global consequences of damping these oscillations. What would it do to seismicity patterns? What are the potential feedback loops? That modeling effort alone would be a grand challenge for the entire geophysical sciences community.
Okay, so decades more of testing and simulation. And if the pilot programs work, and if the models show the risks are manageable, then what? Phase 3?
Then, and only then, maybe from year 51 to 100 plus, could you even consider global deployment and the necessary ethical governance? If the pilots succeed and the models are reassuring, which is a big if, you might start a very phased, very incremental global rollout of this GNet harvester grid, probably starting in the most geologically stable areas, the continental cratons.
And the governance. That sounds almost as hard as the engineering?
It might be harder. You'd absolutely need a powerful international governing body, something like the IPCC for climate change or the IAEA for nuclear energy, but maybe even stronger. It would need oversight over the deployment, the power distribution, the data management, ensuring equitable access and benefit sharing, and most critically, as we discussed, implementing and enforcing incredibly robust fail-safe protocols to prevent that nightmare scenario of catastrophic resonant amplification. The level of global cooperation and trust required is unprecedented.
Wow. Okay, so wrapping this all up, what does this whole exploration tell us? Tapping into Earth-sized standing waves, it's quite a journey.
It really is. It takes us from, speculative science fiction with gravitational waves through energetically impossible ideas like Schumann resonances to something tangible, yet still almost impossibly difficult, with the Earth's own seismic vibrations. While some concepts are firmly theoretical or just don't have the energy, the mechanical oscillations of our own planet do represent a monumental energy resource, albeit one locked behind equally monumental challenges and risks.
Yeah, this deep dive really shows that our planet isn't just some static rock we live on. It's this incredibly dynamic, constantly vibrating system.
Absolutely. And if we ever, generations from now, gain the kind of technological mastery needed to actually tap into these deepest rhythms, the real test won't just be our engineering skill. It'll be our wisdom in managing the profound, interconnected consequences for the Earth's geology, its atmosphere, maybe even its biology. It forces us to think about the planet as a whole system.
So a final thought for you, our listeners, to ponder. What stands out to you most about this incredible, maybe terrifying prospect of harnessing Earth's vibrations? And if we ever reach that point, what ethical considerations do you think would be the most important for humanity to grapple with?